Good afternoon. This is CIVE 638, Sedimentation Engineering, and class number 101, 10-1, meaning 10th week, first class. And I'm Professor Victor Ponce from San Diego State University, Department of Civil Engineering. And the subject today is sediment transport. I particularly like this graph, and I have already shown it to you at least once. But I thought I would start the class today reminding you of this graph and the various components of the graph, because we're going to be actively talking about the components. There are two classifications of sediment load, one based on the predominant mode of transport into suspended load and bed load, and the other one based on whether the particle sizes are represented in the channel bed, and that divides all sediments into wash load and bed material load. So as you can see, there is an overlap. It appears there's only two, but in reality there's three. So to the left of the graph, we have the total division into wash load, suspended bed material, and bed load proper. So the various methods that we are going to be looking into today, as well as Thursday, I believe, will describe the computational procedures to determine, mostly it'll be the suspended bed material load. That's what most equations calculate. Some of them actually include base load, bed load. But none of them, with one exception, include wash load. The only one that includes wash load is the modified Einstein procedure. Now, the modified Einstein procedure is a procedure developed in 1955 by Mr. Colby, who worked the Einstein method 5 years after Einstein had put it together. And we are going to get to talking or to describing these equations in more detail later on. So let me suffice it to say at this point that the subject that we're about to enter is very complex. It's so complex that the elder Einstein told his son in 1928 to get into the field because he felt at the time that there was nobody that knew basically anything about that. And he did, and he became eventually, it took him a few years, but eventually he became professor of civil engineering at Cal Berkeley, the University of California, Berkeley. And he stayed there for 23 years until he passed. I think he passed while he was a professor.
Professor Ponce, sorry, this is Joaquin.
Hi, Joaquin, how are you?
Good, how are you? Thank you.
Okay. Okay, Cynthia's not there, right? Okay. So as I was saying, the elder Einstein recommended to his son to pick up this subject, and he did. He went to the best university in Switzerland, and then eventually they came to the United States. And the younger Einstein, his name was Hans, or Hans Einstein, I believe it was Hans, yeah, got employed with the Soil Conservation Service. And while working with the Soil Conservation Service, he developed this methodology. And then right after that, he got an offer to teach over at UC Berkeley. So that's the story. He's considered to be the most important person in sedimentation engineering, at least in the United States. And we will get there. We will get to his method. I'm not going to claim that I understand completely his method. Can you believe that? Everybody talks about it and nobody fully understands it. But yet, that method, the method is the basis or the foundation for the modified Einstein. And the modified Einstein is a step-by-step procedure, which was put together by the Bureau of Reclamation later on. I believe it was 1965 or 66. It was a step-by-step procedure on the modified Einstein. I'm not exactly sure if Colby did that or not, but it was step-by-step procedure. So then, as the story goes, as history tells us, when I was over at Colorado State as a young rookie graduate student, I was asked by my professor to develop a modified Einstein computer program, which was a high call because it hadn't been done and it was difficult. But we did it. We spent, I don't know, a couple months on it back in the year 1974, 75. And we, I believe, were the first, among the first, let me say that, among the first to develop the computer program for the modified Einstein procedure. Subsequently, in the year 2007, that was how many years? 75, 25, 30 years later. 30 years later, we put it online as an online calculator. So now we have the complete modified Einstein procedure in an online calculator. We could just put the data in there, the 13 or 14 pieces of data, and bingo, get an answer immediately, which in the past, it would have taken 2 or 3 days to do the calculation. And now it's done in 15 minutes with the help of the web and the online calculator and so on and so forth. So that's part of the history. As to methodologies, there's about 50 of them with proper names, so-and-so's method, and they're all different. And there's a graph that Professor Julian from Colorado State put together when he wrote his book. He has a book on sedimentation engineering or sedimentation processes, something like this, where he included this chart that I'm going to show you later on because I thought it was very illustrative of the variability of sediment transport calculations. So we must exercise a little bit of humility when dealing with sediment transport because nobody knows completely everything. Not even Einstein. Einstein's method had a way of failing, by the way. And we were very happy that the boss never asked us to do that because he said that because of that, and it was so complicated that nobody really used the Einstein method. And thank God that the method was actually parametrized into the modified Einstein by Colby, which we could use. And the modified Einstein method is much used in practice. I've received several, I guess you'd say, accolades for developing the methodology and putting it on the web, which allows a lot of people to just go ahead and do it and not have to worry about anything other than the fact that you just press the buttons and you get the answer, which kind of is the way it should be. That is progress. That's what we call progress. Package things and put it into things that are simple enough so other people don't have to worry about where they came from. Okay, so we're going to start with the methods. I'm going to skip this part here because we already covered it at the beginning of the class. You must be familiar. This is the Simon's method, the table. This is the Rouse formula. So we're starting here with the Duboys formula. I believe the pronunciation is Duboys. I'm not French, so I don't know how to pronounce it, but it is kind of a French formula. The Duboys formula is widely recognized as one of the earliest attempts to develop a sediment transport predictor. The Duboys formula is the following. Q sub S is the bed material transport rate per unit of channel width in pounds per second per foot. Psi sub D, a parameter that is a function of particle size in cubic feet per pound per second. Tau sub naught is the bottom shear stress in pounds per square foot. And tau sub C is the critical tractive stress in pounds per square foot. So if you, in the equation tau sub naught minus tau sub C, that is the shear that is actually the moving shear because you're subtracting the critical tractive stress. And that multiplied by tau, which is psi sub D, which is just a parameter that Mr. Dubois developed as part of the method. Now, as I understand it, this method is one of the earliest attempts, and we put that in there because we know this to be a fact. Let me take a quick look at this if you don't mind. I'm going to 14 in here. Oh, jeez. This really surprises me. Not that I didn't know it, I just forgotten about it. The date for the Dubois method is 1879. Analyse de Ponce. That merits a little story. What is Ponce? That's French, of course. I already told you a minute ago that I don't know French, but I know Pont de Chaussée because it's a famous collection of words in French. Pont de Chaussée means bridges and roads. And annales means the annals, the annual, or I can say the yearly report, okay? It comes from the word annum, meaning year. And what is this Annales de Pont de Chaussée? That is the magazine of Pont de Chaussée. Pont de Chaussée is at the time, we're talking 1879 here, would have been among the very few and perhaps the first, certainly the first, but at that time among the very few civil engineering schools. Because it was the French that actually started this engineering, civil engineering in the middle 1700s. So 1753, I think. There's a book written on that, by the way. There's a book on everything. Only you got to read it. I have read the book. 1753, there was a gentleman in France who was a military engineer, because at that time, the only engineers were military. Leonardo called himself a military engineer. Sure, he painted the great paintings, but he wasn't at the time earning his money from painting. He was doing it with military engineering. So suffice it to say that 200 years later, we have this guy working out of France that was a military engineer, and then he found himself doing civilian work. He ran out of military engineering and people were at peace or whatever. And he said, I'm no longer a military engineer. I'm going to call myself a civilian engineer. And pretty soon civilian engineer led to, within a few years, to civil engineer. That's the origination of our profession. In the United States, we use it. In England too. In other places, it's called differently. It doesn't matter. In the United States, in England, it's civil engineer. In France, I believe also. So that's the story of the beginning of our profession, 1753. It is among the first engineerings. It's not the first. Military was first. Then after military, civil engineer, and then came mechanical, then electrical, and so on and so forth, paralleling the development of society in the 19th and 20th century. That we know. I'm really surprised because I thought that Dubois was old, but not that old. This shows already he's 140 years old in terms of the development. Okay, let's go back in here. So we got this equation over here. And this equation merits a little more time for us to study this topic. The psi sub d, it's a fudge factor. We got to consider that. I'm not going to call it a fudge factor. I should call it just a parameter, because fudge factor implies that it's not right and you're trying to figure out something to do. But look at the construction of this equation, tau sub naught times some function of tau sub naught. So basically, this brings up, with the exception of the tau sub c, it brings up the tau square. There's a tau square in there implicit in the equation. Okay. Now, interestingly, though, the theory tells us that the sediment transport is a function of tau times v, velocity, the velocity times tau, because tau times v gives us, since tau is a product of v square, is a function of v square, so tau sub naught times v would give us a coefficient of v of q, v squared times plus 1 is q, which essentially says that the sediment transport is a function of the velocity, the mean velocity to the cube power. So Dubois is making here an exception in here and making it to the fourth power. Can you see the fourth power in there? It's tau times tau, and tau is already squared to v, so that's fourth power. So having said that, okay, we're going to come back and say that we have extensively studied this subject, and we realize now, as following Colby, by the way, our friend Colby, that there's a lot of truism behind the formula to the cube power. So it's certainly not the square power. The square would be strictly shear. The Q power would be the beginning of transport. And the fourth power would be Dubois's. But there's also fifth and sixth and seventh power. Those are the Colby formulas. So as you can see, Dubois was not too far away from it. As a matter of fact, I'm going to say that he's almost precisely on the money, because the velocity 3, the Q power of velocity, is a transport under, how am I going to say that? Under low transport, the low transport. No, I'm sorry, I take that back. High transport is the Q power. But then when the transport starts lowering down, it'll go up to 4, 5, 6, and 7. So it is no surprise that Dubois was doing some measurements kind of in the middle of the range, and his exponent was 4, and it was not 3. I'm not surprised. I think that would be the case. And it justifies everything we have said so far, as well as the findings of Colby, which we are going to describe later in more detail. So that's the Dubois formula. Now, the Dubois formula is kind of intricate in its computation, if I could call it intricate. I'm not going to try to scare you here. But basically, the procedure is here. The procedure is here. Well, we got to figure out what the size of D is, and the size of D is in this graph, right? This is the size of D varying with the mean diameter, which is the way it should be, because the mean diameter is the essential factor. So based on mean diameter, we have a size of D, and then we got the tau sub C. We got the tau sub C. No, I'm sorry, I take that back. The tau sub C is this line over here, and it's to be read in the left side of the graph, of the ordinates. And the size of D is to be read on the right side. So what I would do if I had to apply this, I would go to the mean diameter, to the size of D over here, and bingo over here, and pick up a number. And then I would go to the tau sub C and pick up the number over here, right? And then I will get the the size of D and the tau sub C over here. And where's the tau? The tau is defined already. Tau is gamma ds. That we know. So it's done. Done. And I'm going to let you go into the details, because I have already explained it over here in detail. And then, of course, there's a calculator for it. We have a calculator just about on everything that we can calculate. There are more than 300 calculators, but 100 of them, 120 of them in English. We also have Spanish and Portuguese, because I spent a lot of time in Brazil in the 80s and middle 90s, about 15 years. And not only did I learn Portuguese, I did a lot of work, and I learned a lot of the work in Brazil. So I kind of like that, the fact that I was there. I was lucky that I was there. I think I already told you, I was recommended by one of my professors to go over there and get started. And once they knew me and I knew them, we continued to work for several years, like 17 years I worked in Brazil. Okay, this led to our studies on the Pantanal and these other studies, at any rate, which you heard me talk about in perhaps not this class, but other classes like environmental engineering and so forth. I'm sorry, not environmental engineering, environmental hydrology. Okay, so that's the online Dubois. I wanted to say something, that in order to develop an algorithm or a script, it's also called script, by the way, it's a new word, the script. It used to be called computer program. Then people, some reason, don't like the word computer program, so they call it an algorithm, a computational algorithm. And lately, in the last 10, 15 years, they've been calling it script, for whatever reason, I don't know. So in order to develop the script for this formula, you have to put these equations into the computer. And he didn't give them to you. He just said, here's the graph. And all we did was we put together his graph and added some color and a little bit of clarity into the graph. That was all. Because that's basically his graph, right? So in order to do that, we have what it's called, well, the size of the line, it's a straight line, obviously a straight line, so that's easy to put in the computer. The other one is not straight, so that's not easy to put in the computer. There's two ways to do that. Either you use the so-called methodology what is it called? Fit a line, a curved line. You can fit on any set of data, a curved line, and it can be done. There's software, various software to do this, by the way. Actually, this methodology is called, in mathematics and in statistics, is called a spline, S-P-L-I-N-E. You may have heard of that. I believe even Excel has spline calculations, a very common thing. But the spline has a problem. The problem with it, I don't like. The problem with the spline is that it fits a range very nicely, but if you're out of the range that you fit it, then it doesn't fit, or it fits poorly. So we, over the years, found ourselves confronted with the fact that we had to do a lot of these. And we looked at the splines, and the splines weren't working, and it was kind of hard. So we devised what we call the piecewise linear interpolation. What does a piecewise linear interpolation do? Well, we come in here into this line that you see in here, and we put in there lots of points, like 100. 100 would not be uncommon, by the way, because the computer's going to do the work for us. So we put 100 lines in here, and then draw a line between two neighboring lines. Between two neighboring points, we draw a line, and we express that line as a line. And that's it. So then when we start doing a calculation, we go to the respective line and we get the exact number. No deviation whatsoever. And we have this algorithm that we use since I believe it was, when was it? It was since my book, 1989, 87, 86, 87, 89, we developed this. We even were so confident of that stuff, we actually put it in our book, the algorithm. People were doing that at the time. Nowadays, they don't like to do things. People don't want to publish code anymore, but we used to. Oh, we publish code. I got stories to tell you later on. When you publish code, people can copy the code and run with it, which is fine. But you lose the property of the situation, right? You can't say, I did it and nobody else has it, because they've copied it and they have it. So we people may actually reproduce what we did. I don't know. But it's in my book, in my blue book, because I have two books of hydrology. The blue book, which was printed in 1989, printed copy. And then there's the web online, which came in the year 2014. So 89 and 2014, 89, 90. So that's 14, 20, 26 years later, we put the book online. That's another story I'll tell you about later. So that's the methodology by Dubois. Meyer-Peter formula. Meyer-Peter was, I believe, a gentleman, if I remember correctly, working out of Switzerland. And he developed this formula, which is a very well-known formula. Interestingly, though, it's for gravel. It's for gravel. Gravel loads, because gravel is heavy, then the river has to spend more energy carrying the gravel. So the gravel values are generally low. They give you a low value. The predictors let me put it that way. Meyer-Peter formula, which is a predictor for gravel, usually misses on the sand because it tells you that it's much less. And there is a graph on that I should show you in here. Let me see if we can find it. There it is. There it is. Look at the Meyer-Peter here. Meyer-Peter Mueller and Meyer-Peter. There's actually two. And we were talking about, I believe, the Meyer-Peter Mueller, and it's still low compared to all the others. Can you see that? Those others are high. As a matter of fact, I mean, the ratio between this is 2 and this one's is 2. So the Meyer-Peter Mueller is giving 1/10 of the results of the other path on top of it, of which the Akers-White and the Colby are considered to be the big ones. Akers-White is the one that's considered to be most accurate. It's over here, right in the middle of the pack of the lots of answers in there. The center of the formula. Okay, so that is the Meyer-Peter formula. And it also has a calculator. And the explanation is in there. The explanation on how to do that. I'm going to leave that for you to do because you should review how it was done. And like I said, in our examples, everything is clear. You can pick up a pencil and paper and find out that exactly we did it correctly. Because if we made a mistake, you should tell me. You should call me up or send me an email saying, Professor Ponce, I do not believe your result or in your book is correct. Has that happened before? Very unusual, maybe once or twice, but not more. But every time I've had somebody call my attention on an error, I looked at it, confirmed that indeed it is an error, fixed it, give him the thanks to the person and run with it. Nobody's perfect. As a matter of fact, I had a couple of my calculators. I said 300 calculators, right? A couple of my calculators had mistakes. Had one mistake was very important. It was a conceptual mistake. The other one was not so much a conceptual mistake. It was just a detail that I'd failed to add the detail in there. But it was caught by people that actually are following this stuff. I had a professor over in Bolivia who originated in Holland, I believe. Yeah. And he went through the painstaking exercise of checking this particular calculator, which I had done for culverts, for culvert calculation. Culverts, you know. And he told me, he says, there's a mistake in there. So I promptly, he's a friend of mine on top of it, a colleague and associate, because I've done some work in Bolivia too. But at any rate, I was able to fix it. So that's the bed load function, rather not the bed load function, the Meyer-Peter formula. Again, I repeat, there's a Meyer-Peter-Mueller and the Meyer-Peter formula. I got confused a minute ago there. There's slight differences between them, but they both developed by Meyer-Peter out of Switzerland, and they were dealing with gravel. Why dealing with gravel? Because Switzerland is high. It's got a lot of mountain creeks where gravel is predominant. So it's not uncommon that would happen. So typically the Meyer-Peter-Mueller is a gravel predictor, as opposed to the Colby method, which is sand predictor. Okay, Einstein bed load function. We are already extensively covered Einstein. Let me get a sip of water here. In 1950, Einstein published a procedure for the computation of bed material transported by size fractions. I have read the Einstein paper many times. I don't know, maybe 20 times. Not to say that I understood everything. When he gets into the statistics, he gets Professor Ponce lost. I am a lot of things, but I'm not a statistical person. I remember when I had to take statistics at school, at PhD school, I suffered through it. I thought I was going to flunk. But I said, no, I'm not going to flunk. And I dedicated myself to studying, and I studied a heck of a lot of time. And I passed with an A, by the way. I couldn't believe that I had done that because I don't like statistics. But I had to do it. They forced me to do it. They said, you got to do it. That's part of the requirements. So I did it. The math was somewhat easier for me. Math's always been easier. But the statistics, I don't like. At any rate, there's a couple pages in the 50-page book of Einstein where he deals with statistics. Okay, so but we're going to get there. We're going to get there. Einstein is credited with the introduction of several novel concepts in sediment transport theory, including the separation of boundary friction into grain and form roughness. Right, grain and form roughness, which Simons did, but Simons' work is dated 1957, and Einstein's is dated 1950. So that was 7 years earlier. But Einstein had been working on this for more than 10 years because it was in the middle 30s that he got his degree, his PhD degree at Swiss Federal Polytechnic. And then after that, he went to the United States. He came to the United States for political reasons. I'm not going to get into details. But then eventually he would have come into the United States around 1938. And in 1950, we find him working for the Soil Conservation Service. So what happened in those 12 years, we don't know. But that led to Einstein studying, of course, a subject and eventually becoming knowledgeable on the subject of sediment transport. His paper is interesting to read because it reveals a lot of experience. So minus the part of the statistics and how can I say, the detail that he put into that paper is really kind of amazing because he developed some integrals. And then he developed some graphs, and you had to go into the graphs to find the values for the integrals, which we, by the way, did. We had to do. If we were going to solve the problem, of the modified Einstein, we would have to get into the Einstein graphs, which we did. I'll get that. I'll get there eventually. Okay, so Einstein's bed load function first computes the bed load transport. Then it uses the bed load transport to aid in the integration of the product of the suspended sediment concentration profile and the flow velocity profile. Don't forget that it was Rouse that actually came up with these values much early. Rouse precedes Einstein. Rouse, I believe, was writing his book in the 1940s, early. Rouse was a professor of civil engineering at the University of Iowa, and he's considered widely regarded as the originator of hydraulic engineering. I don't know if that is precisely correct, but he's very much respected. Hunter Rouse, I believe. So that's basically it. He used the Rouse formulas and so forth, and he integrated. There was integral formulas in there because you got to sum up across the vertical velocity profile and the vertical concentration profile. And since the transport is velocity times concentration, then you got to do mathematics in there. Okay, that's the Einstein method, and we will get there. We'll get there probably in a week or a little more. At the end of this section we have this section in 3 weeks, 2.5, because next week it's a short week. The modified Einstein now. This is the important one because this is the one that is being used in practice. I do not believe the Einstein method as such is used in practice. And that is the reason why Professor Ponce has never attempted, because it would have been a waste of time for me. I know what a waste of time is. For me to attempt to do a calculator, an online calculator for the Einstein method, because nobody's going to use it. That's problem is what Colby tried to fix. He said nobody's using the Einstein method, but he fixed it, made it easy, made it simple, understandable, and then everybody uses a modified Einstein. So the modified Einstein was developed by Colby and Hembry in order to include actual measurements. Now that's number 6 in our reference list. Colby and Hembry number 6, 1955. So it only took Colby and Hembry 5 years after Einstein had published his report to come up with the method. Colby. There you go. Typically, measurements of suspended load do not include A, the bed load, and B, the fraction of suspended load moving too close to the stream to be effectively sampled. What does that mean? Well, in plain words, it means that the measurement, the sediment sample, the measurement of a sample of sediment does not include the bed load. Because if it does touch the bed load, it will disturb the bed transport, and then you wouldn't be able to measure anything. So it does not touch the bed load. And for that matter, it doesn't touch the suspended load, which is in the proximity of the bed load. And that is a certain amount in feet, maybe 0.2 feet, that the sampler does not get there. So what they have to do, and they have done rather successfully, is extrapolate the curve. They know the shape of the curve, so they're going to extrapolate the curve below the depth at which the sampling is stopping. They stop the sample at a certain depth near the bed, and then they extrapolate in order to get to the bed. Plus, they have to also calculate the bed load, which is what Einstein was doing, by the way. That was the major attempt or objective of the Einstein method, to calculate the bed load. So that's the way they did it. I am sure that Colby and Hembry spent a lot of time doing this. I wouldn't be surprised if it probably was the 5 years or 3 years after Einstein developed his method. These things look easy, but they are not easy. I was close to the Vedelnikov number in the year 1977, and I didn't see it. Why? I didn't see it. And then several years later, I was being confronted again with the Vedelnikov number. And then I started seeing it. And then in the year 1991, that was 14 years later, I wrote that famous paper on the perspective of the Vedelnikov number, which gave me a lot of accolades, because I was the first one that came out and clearly spelled everything about the Vedelnikov number. So prior to the 1991, the Vedelnikov number was a mystery. so much a mystery that Chow had decided to hide it in his book, and he successfully hid it for more than 20 years. That's worth the story, which I will tell later on. I tell that story to my students of open channel hydraulics, but this is not an open channel hydraulics class. So at any rate, it took a while for Colby to get there. And then in 1957, see, look the progression in time. 2 years later, Colby said, oh, this method is good, but you need a measurement. But it was good. It was a good method. He felt confident that there was a good predictor, and therefore he developed his own Colby method, 1957. And why is it called Colby 57? Because later on, he thought he was getting smarter and gave away with the measurement and came up with a methodology that was not going to use any measurements, which meant that it was going to be used a lot. Because the fact that there's the presence or absence of measurements limits the applicability of the method. If you don't have any measurements, you cannot apply the method. But long story made short, Colby developed the 1957 method, which is based on measurements. And then seven years later, he developed this Colby 64 method, which is entirely based on hydraulics. So first, let's take a look at the Colby 1957 method. I should also tell you, or you should surmise at this point, that Professor Ponce is going to come up with a calculator to do any method, particularly these methods that are very simple to program. So we have a calculator for the Colby 1957 method. The method is kind of cumbersome. It requires 3 graphs, and you got to go in there, and they got names, and they're like uncorrected, unmeasured sediment discharge. Then you correct it, and then you come into the measured value. So it's, for those of you that don't have experience with sedimentation engineering, which I'm assuming many of you or all of you don't, it's going to be kind of, you're going to have to be paying attention when you read this and are trying to understand what he did. And I'm saying this because I've done it many times, and I still wrestle with it. It's not easy to understand because of the way he put it together. But eventually you do it. And then once you understand how it does, then you don't have to worry about it anymore because you got the calculator that will do it to you in 1 second. But the point is that he developed the Colby 57 method based on some of the same measurements that led to the development of the modified Einstein procedure. So he was trying to simplify even the modified Einstein. Because the modified Einstein was time-consuming, very time-consuming. I would say a couple of days. You got to spend a couple of days looking at the charts, getting all the data, and God forbid that you make a mistake in looking at and taking a look or analyzing, taking data out of any one of these 12 graphs. Einstein had 12 graphs, and you got to go into all 12 in order to get the number. So that would take you 2 days. Well, not 2 days, but let's say a lot of time, depending on how many times you did it. If you did it for the first time, it would take you more than 2 days. But if this was something that you were doing in and out on a daily basis, you know, the mind gets used to things. Repetitive things, minds get used to it. So it would have taken maybe a few hours to do. Not anymore, because we did it, we put it on the computer. As a matter of fact, and now I'm going to reiterate, we put it on the computer as early as 1975, 76, because Professor Mahmoud told me to do it. He says, what are your job, Ponce? He said, I know you're good with the computer. That was interesting. When I signed up with Mahmoud, he said, Ponce, we're going to do numerical analysis here. And I'm assuming that you know Fortran. And I said, yes, I will, immediately. I knew little Fortran. I was coming directly from the field, but I knew that I had to do it, and I knew that I could do it. I had delved in Fortran earlier, you know, and I did it. I became an expert in Fortran. So much of an expert that we wrote a book in 1992. And it was an interesting time for, I don't want to sidetrack in here. Let me just say that I'll come back and finish that story later on. So it is a long story, by the way. So we got in here the measurement. So he is going to do the procedure as follows. First, use figure 13.2, like this one, right? It's a straight line, to obtain the uncorrected, unmeasured sediment discharge as a function of mean velocity. That's easy. The hydraulics already know. Use figure 13.13 to obtain the relative concentration of suspended sands is a function of mean velocity and flow depth. So you got to go abscissa to any of these charts in here, and then you have the relative concentration of suspended sands. Then calculate the availability ratio by dividing the measured concentration of suspended bed material, C sub m, by the relative concentration of suspended sands. In other words, the data is already there. The C sub m is already known. It's a measured concentration. And the C sub r is the relative concentration which we just calculated a minute ago. Relative concentration, that's right there. And then use this chart in here using the mean line and the so-called availability ratio to obtain the correction factor C, from the availability ratio, which we have already calculated. If you think this is kind of cumbersome, so be it. That is Colby's method, not mine, okay? And why would it be cumbersome? Because the problem is a complex problem. This is sediment transport, it's complex. So you get the correction ratio, correction factor, and then you apply the formula that says the unmeasured and the measured corrected. The correction factor, the measured and the unmeasured discharges, and the 0.0027 is to convert the proper units, 0.0027. And I believe I'm going to give you an example. At the end of the class, when we talk about measurements, I'm going to ask you to develop the 0.0027. It's an exercise in handling units, which we should. We should be good at handling units, because if we don't, then we'll mess up. Particularly since we very often have to convert between US customary and SI units. We should be conversant in both, by the way, because while the United States uses US customary units, the rest of the world uses, with some exceptions, uses SI, which is the metric system. The old metric system has now been referred to SI. There's 240 countries in the world, and my guess would be that, I don't know, my ballpark figure, maybe 220 of them use the SI. Google it. Go Google, so how many percentage-wise countries in the world use SI? They're going to tell you, and it's going to be fairly accurate. Google, in my opinion, is 98% accurate. There's always an error in there, but it's too small an error for us to worry about, given the practicality of the answer, quick answer. Okay, so this is the methodology, and this is the example, and it is very clear in there. You should have no trouble following this. Absolutely. And then we have an online Colby in there. Let me do this. Let me run this in here. I'm just going to plug in some numbers, okay? US customary, flow depth in feet, say 5 feet. Mean velocity, say 3 feet per second. Channel width, maybe 20 feet. And mean concentration of suspended bed material in ppm, let's say 500. So the total bed material discharge Q sub S, 626 tons per day. How easy could this get? It was like a fraction of a second, right? Because we have very, very big servers. The servers of these days are extremely fast. It didn't used to be that way. When I started my career in the year 1967, the size of the computer of those days, it was called the IBM 1130. And the size of the computer was, I believe it was 7K. 7K. Kilo. Then we went from kilo to mega, from mega to giga, and now we're from giga to tera, I believe. So each jump in words was 1,000. So a million, a billion. So the size of the computers nowadays is more than a million and less than a billion, because we still don't have the computers that have teras of capacity. I think that my servers are running now at 32 gigas. So it'll take a while before they get to the teras. The teras are considered for the issue of storage, not for RAM, right? But let me just go back in here to show you that, in fact, we did that calculation and we're done with the Colby 6057 method. So now we're moving into the Colby 64 method. This is the method that my professor, Daryl Simons, liked for various reasons. One of the reasons, the primary reason, is that Colby is a very well-respected gentleman. He was, I believe, employed with the Geological Survey, but I could be wrong on that. We need to go back to his bio data. A very well respected gentleman. He knew what he was doing. He was trying to simplify the calculations because the calculations of the time were extremely time consuming. Don't forget that even at those times, we still didn't have the calculators, the electronic calculators. The electronic calculators came to the market in the year 1968, right after I finished my engineering career. So while I was in engineering school, I was not using these calculators. You know what we were using? I should tell you, just for the sake of curiosity. You were using the slide rules, which went, of course, away the dinosaur the minute the calculators came about in the year 1968, 69, 1970. I believe it was in 71 that I first grabbed and got a hold, or I bought a calculator. It was the HP 35. You guys probably don't remember that because we're talking here 52 years ago, right? But right after that, we have the electronic calculators, and then now we have the computers and the online calculators, which, by the way, we kind of started in earnest in the year 2005. And unfortunately, not too many people, as far as I know. And when I say as far as I know, it is as far as I know. As far as I know, not too many people have actually caught on to this and taken it. And why is that? Because people are comfortable with Excel, even though Excel is 32 years old. It came out in 1990, 1991. Yeah, 32 years old. And it is not amenable to online work. And yet people are, I'm not going to say anything, but all I get is enemies if I say something. So let me just keep quiet at that point. So let me just say that Colby 64 method was a good method. It was Colby's mind, product of his mind. He tried to simplify things. He was not going to deviate too much from modified Einstein, which he had created, which did not deviate too much from Einstein. So this whole thing comes from Einstein. The beginning, the root of this whole thing is from Einstein. So in 1964, Colby published a method to calculate discharge of sands, bed material discharge in sand bed streams. Let's say this, discharge of sands. So can Colby method calculate gravel? The answer is no, absolutely no. It only calculates sands. And it only calculates sands of a certain size, not too coarse and not too fine. The depths are already established. As a matter of fact, the depths are between 0.1 and 1 millimeter. Median size of bed material, for corrections in here, 1 millimeter and 0.1 millimeter. So these are the medium size sands. Why did he do this? Because he found himself doing transport calculations in the Midwest, I would say, it was the Niobrara River in Nebraska. And he was doing calculations in Niobrara, I believe. It has to be. If it's in Nebraska, it's got to be a tributary of the Missouri. Don't get me on that. It has to be, because that's the only large river around there in Nebraska. It's the Missouri. Okay, so it's a tributary of some tributary of the Missouri. Okay, and he did all his measurements in the Niobrara River, which was sand bed channel. And so his measurements reflect that. Nevertheless, it has wide applicability because a lot of the rivers that we work with are in the sand bed channel, just like his Niobrara River. Why is that? Well, this is a fascinating story in the fact that most analysis and development is in the valleys, in the middle valleys, not too much in the estuary and not too much in the mountains. In the mountains, we're going to have gravel, and in the estuaries, we're going to have silt. But he wasn't too concerned about it because most of his work was in the valleys, in the mid-valleys, where the size of the bed material is of that kind, 0.1 millimeter to 1 millimeter. The story as to why is he using millimeters when he should be using SI units is a fascinating story. And I truly honest do not know the answer. But look at this, this is odd. First he's saying, let's talk about feet per second, and feet and so forth, and velocity, feet per second. And then by the time he gets to this graph in here, he's talking millimeters. Why is that? My best understanding of the situation is that they did not want to talk feet when it came down to the diameter because it was too small. And they felt uncomfortable with using 0.003 feet. That was kind of cumbersome, right? So that's why they did it. So the millimeter crept into the methodology, even in the US customary system, as a predictor, or rather way to measure grain size. So we had to get used to the millimeters. Okay. The development of the Colby method was guided by the Einstein bed load function and supported by large amounts of laboratory and field data. The method has been shown to provide a reasonably good prediction of sediment transport rates, particularly for sand-sized particles, right? The data that for which it was developed. The following data are required. And by the way, this methodology has the advantage that it is encased, it is well behaved, because you're not going to get a wild number out of this method. Why? Because you're going into these charts, and there's no way that you can get out of the chart. Really, simply no way. What are we plotting in here? He said the following: the sediment transport is going to be a function of the mean velocity. Yes, correctly. So that's why he has 4 scales in here. But then he said it is also going to vary with depth. The greater the depth, the greater the sediment transport. So for 0.1 feet, which is nothing, 0.1 feet is 1 inch. So this laboratory flumes right here. 1 foot is fine. 10 feet is more normal, and 100 feet is wild, because that's already high. 100 feet, not even the Mississippi has 100 feet. I think the Mississippi's depth is around 50, 60, 70 feet. Although the Amazon has more than 100 feet. The measured depth of the Amazon at OB2 is about 60 meters, 60, 70 meters, which is 200 feet. But yet I have seen measurements or reports of places where it gets to 90 meters, 270 to 300 feet. So the Amazon, undoubtedly the deepest, and I guess you could say the meanest, probably. Why did I say meanest? Well, how does it, one has to do with the other? Well, the Amazon is so deep that it has this huge fish that will eat anything, including you, if you happen to fall off board out there, unlucky, and it happens. Not so often, but it does happen. It's huge. They're about, the size is about 10, 12, 15 feet length fish out there in the depths of the Amazon. Don't remember the species at this point. The locals call it the paiche, but it has the various names out there, because apparently there's several species of that monster. Okay, it is a monster. Okay, so that's the method here. So now we go back to Colby's method. The following data are required. Mean flow depth, yes. Mean channel width, yes. Mean velocity, yes. Water temperature, yes. Why do we need water temperature? Because the viscosity is always affecting the transport. The more viscosity, the less transport. Concentration of fine material load. This is interesting. First, we said that the concentration of fine material load had nothing to do with the transport. And now we're saying that it does. Where's the truth? The truth is that to say that it has nothing to do with the transport is a misnomer, or is not quite correctly stating it. Theoretically, it shouldn't when the load is low, but if the load gets high, then it does. It interferes with the transport. Let's put it that way. So then Colby saw fit to put into his method the concentration of fine material wash load. And in doing so, he was the first and only person that put the concentration of fine material wash load, the C sub W, into any methodology. So at that point, we should then reiterate that the Colby method is the one that does it. And also the modified Einstein, by the way. Modified Einstein does it too. Okay. And median size of bed material, that is obvious, the transport is driven by the bed material size. So the procedure is as follows. We have these tables in here, which I love. And the reason why I love these tables is because they justify a theory that we have, which I'll talk about later. We have plenty of time to talk about that. So I'm not going to talk about it today. But suffice it to say at this point that these graphs show a story that I like. Actually, I love because I've written papers on this subject. So use figure 1315 to determine the uncorrected discharge of sands, Q sub U, uncorrected discharge of sands. That's in the ordinates, in tons per day per foot. It's not very clear there, in tons per day per foot. It's a function of mean velocity, flow depth, and sediment size. That means the hydraulics and sedimentology. We have the sediment size, we have the mean velocity, and we have the flow depth. We should get that. The sediment size is measured from the laboratory. And this is interesting, the laboratory. How do you measure sediment size? If you were doing this from a geotech standpoint, geotechnical engineering, you would use sieving. But the hydraulic engineers don't like that because it's too consuming and it's not, the accuracy at that point is really not absolutely necessary. So they use the so-called visual accumulation tube, which we are going to briefly talk about later on when we get to the area of measurements. Visual accumulation tube that was developed in 1955, and I believe it was Colby also that had something to do with it. I could be wrong on that, but we'll go back to the original reference on the visual accumulation tube, 1955. So with that, we determined the diameter, the D50. So with the D50, the depth and the hydraulics is already known. The hydraulics is already known, so we go in there. For instance, in this case, let's say the mean velocity is 3. We go in 3 in here. Let's say the depth, or rather the size is 0.5. We go here to 0.5. We're kind of in a cloud in here of data. So we're going to get a number in here. We're going to get 20, 30. We get 30 tons per foot, tons per day, tons per day per foot. If we were over here, it would be easier. I mean, easier to get the number because the cloud is more dispersed and over here. But notice, I was noting this morning because every day I teach, I actually read the stuff in the morning. And I was noticing in the morning that I actually never actually observed the fact that I'm going to say today, that the two graphs on the right are largely extrapolated. The two graphs on the right are largely extrapolated, meaning that if you're really going to have confidence in the data, you should restrict yourself to the first two graphs, which are kind of small. You see the extrapolation there, but he did it, and he was confident that he was going to do it more or less correctly. And he was the first one that was coming up with this kind of methodology. So he felt that no matter what it was going to be useful. So we got this extrapolation in here, but according to Colby, it was good. And we get the number of the uncorrected discharge of sands in tons per day per foot. For water temperature of 60 degrees Fahrenheit, negligible wash load concentration less than 1,000 ppm. Let's talk about this a little bit more. Negligible wash load concentration less than 1,000 ppm. So what's 1,000 ppm? How does the river look with 1,000 ppm? Okay, the river looks a little brownish, but for 300, 500, actually clear, more or less clear. But by the time it gets to 1,000, it is already looking like chocolate. And if it gets to 3,000, it will look like latte, coffee, you know. And so 1,000 is not high and is not low. So he used that number for whatever reason, 1,000 ppm. I should tell you that normally the normal background value for this wash load concentration around the world is around 300 to 400 for the wash load. Actually, I'm going to take that back at this point. I made a mistake. For the total sediment load under normal conditions, you're not talking about rushes or carrying during rain. No, just normally it's 300, 400, out of which a portion of it is wash load. Okay, at any rate, what he said was that if the wash load was less than 1,000, you're not going to do a correction. No further corrections or calculations are required. So what you got out of the figure 1315 is the correct number. For conditions other than the preceding, in other words, for water temperature different than 60, wash load concentration greater than 1,000, and sediment size in a range different than between 0.2 and 0.3, which appears to be the central range of his values, of Colby's values, then you got to come up with a correction. And the corrections are K1 for water temperature, K2 for concentration of wash material or fine load, wash load, and K3 is a function of median sediment size. So these are the charts. They're not very clear charts, but they're charts nevertheless developed by Colby. So what are we doing here? We go to the depth and we go to the temperature. For 60, no correction. It's in the axis, 1. For 70, it's a little less. The correction is less. The K1 is less. K1 for 100 degrees is much less. It's almost like for 100 degrees and the depth of 100 would be 2, 3, 4, 5. So 0.57 over here. 0.57. Now that's for the K1. For the K2, likewise on the left in here. But now we're going to go from 1,000. For 1,000 is nothing. No correction. 10,000 over here, 20,000, 30,000, 40, 50,000. What are you talking about here? 40,000 watch load? That's a heck of a lot. I already told you that by the time we get to 2,000, it's going to look like coffee. Not coffee, like latte, like, with milk in there. It's a little whitish thing. But the fact of the matter is that the heavy wash loads are part of what we call debris flows and high concentration, high sediment concentration loads. Anything about 50,000 is already considered our high sediment transport. 50,000 is over here. So we can get all the way to 140, 120,000 numbers, extreme numbers of 200,000 have been seen in this sense. Although Colby never got to 200,000, presumably because he never felt it was necessary. But 140, roughly very close to 200,000. So he makes these corrections against the K2. And for the K3, he deviates from the 0.2 to 0.3 over here. Anything less than 0.2 will have a correction, K3 less, likewise greater than 0.3, also correction. If you get to 1, the correction is extremely high. If you get to 1 over here, the correction K3 is 0.06789, 2, 3, 4, 5, 0.56, 0.056, so that's 5% only for the K3. But the situation is not linear. If it were linear, then it would affect it. But if it's not nonlinear, it depends on the shape of the nonlinear equation. And the nonlinear equation is over here. The discharge of sands given by the following formula, as you can see, is not linear. It's not like saying, oh, we're going to cut it. We're going to cut a slice of it. No, it's like this. And that's his formula. Nobody can change it. It's his formula. And nobody's ever touched this formula since 1955. Presumably it works. Okay, so that's it, the discharge of sands. And likewise, we have the example and we have an explanation of where the numbers come from. So that should be an easy matter for you, no difficult matter for you to proceed and learn how this thing is done. And finally, we have the Colby method. And I'm going to run a US customary in here. Mean velocity 3 feet per second, mean flow depth say 8 feet, channel width maybe 20 feet, and water temperature maybe 68. That's 20 degrees Celsius, 68. Wet material size 0.7 millimeters, and wash load concentration, let's say just 500. Calculation. Colby, oh, we made a mistake here. Wet material size is out of range, 0.1 to 0.9 millimeters. Oh, I'm sorry. I'm sorry. I didn't put a period in there. I forgot to put the period in. The computer not going to like it. And our systems are designed to not to make a mistake, a gross mistake. It will make if you put in there 0.7 instead of 0.6, the computer not going to catch that. But if you put, like I did, without a period, it will. And it did. So the results show 194 tons per day. 194 tons per day total, because per unit width is 9.72 tons per day. So that's an example of the Colby calculator. I should tell you, as we move along here, one story, which is kind of a like story because it relates to me. I already told you that in 1976, I was charged with doing, no, I was 75, charged with doing the modified Einstein, and we did it. And we published a computer program. By the way, that computer program has been published because at the time, we had no problem in publishing code. We did the code and we were so happy that we had done the code. We tested the code and so forth, and we published it. The publishing of the code means you're going to put it in some place where people can copy it. But it's in books, so they got to fax it, or rather scan it and then clean it up and so forth. It's not easy, but it can be done, and it's been done, by the way. So so that's the way it's done. Now, subsequently, though, in the year 2007, I spent some time converting it to PHP in order to convert the Fortran to PHP, because that was the thing. PHP had already been invented and so on and so forth, and that's what we were doing at the time. So we developed the PHP code, which we now have, which is the one we just ran a minute ago. We ran the PHP code. The story about this PHP stuff, vis-a-vis Fortran, is an interesting story, which I think you guys should know, by the way. So I'm going to dwell on it right now, particularly because we are knowledgeable. Fortran developed in the year 1954-55. It was the first, they call it non-machine language code, meaning normal engineers could understand it. And it became very popular to the 60s and 70s and 80s. And one of the advantages of Fortran, or characteristics or qualities of Fortran, is that it's an extremely fast program. So fast that it has not been matched even with the programming tools of these days. Fortran is the fastest. Why? Because all it does is computation, what it's called floating point. All it does is computation, and it does it very well. Any other programs that subsequently came about do all kinds of things. They don't specialize in just computation, they do everything. They have to do everything, because nowadays, 99% of the computers installed all over the world are in your palm, in your cell phone. There's so many cells. I think they say that there's 5 billion cells out there, cell phones out there, and growing up very quickly. Very quickly, it's going to get to a cell phone per person in the world, and if it hasn't gotten there already, okay? So the computers that we use nowadays are in your palm, in the cell phone. 30, 40 years ago, it was not like that. In 1980, San Diego State inaugurated they purchased a VAX computer, DEC digital equipment, which used an entire large room out there in what used to be called the Business Administration Building. I think they paid $5 million for the computer. And I love that computer. We used that computer several years, maybe through the early 80s, 80 to 85. That was the way for us to compute at that time. It was only in 1990 that the PCs came about and they started eroding on the market of the VAX so much that digital equipment died in the year 1995 because they could not compete with the PCs. So that's the story. I'm telling you so that you know. You should know the story. Now, so that's the Fortran. But it was not superseded because nobody has been able to find a faster calculator. But since people don't use the computer just for floating point, then it kind of was relegated to second or third, okay? Now, it is still there, and you can still do a calculator, an online calculator, using Fortran, but it becomes cumbersome. Since the year 2000, we have better tools. Particularly in the year 2000, the PHP language was developed in, I believe it was in Switzerland or somewhere out there in Europe, and it took over. It took over. I used to do programs in Fortran that were online, but I realized that that was not the way to do it. So we did the PHP. And admittedly, the PHP programs are slower, but they are easier and friendlier than the Fortran program that we had to do dinosaur type, at the beginning of the situation. So I would say that Fortran was relegated in the background. People that don't know, ignorant, say that Fortran is dead. You guys should know that when you run RAS, which you will, If you're an engineer, civil engineer, you're going to run RAS. If you run HMS, which you will if you're a hydrologist, Fortran is running in the background. And that's why RAS and HMS are very fast. If RAS and HMS were running PHP, it would be 10 times slower. I guarantee to you, I happen to know what I'm talking. 10 to 20 times slower. And you get bored out there waiting for the answer. Well, Fortran, boom, like in half a second already gave you an answer in RAS, in HMS, and so forth. So you should be thankful to the old technology, the oldie but goodie technology, such as Fortran, and not say things that are not correct, because it's been said, by the way. That's why I know that. So that's basically it. And I'm going to finish in here. I got 3 minutes. I'm going to show you this chart that I already shown. This was part of, I believe, let me see, number 26 reference. Julian, Erosion and Sedimentation, Cambridge University Press. Professor Julian, Colorado State, wrote a book in 1995, and he added this chart in here, which I thought was very good. And as you can see, we put in there 2, 4, 6, 8, 10, 12, the most widely recognized equations for calculation of sediment transport. How many are there? There was a gentleman by the name of Whale Williams, who happens to be my colleague, my friend. I don't know where he's right now. He used to be the head of West Consultants in town, but then he retired, I guess. He did a dissertation over at Colorado State in the middle 90s, and he compared 50 methods. So that's why I happen to know that there's 50 proper name formulas for sediment transport. Julian has put in here only 15 because those are the most knowledgeable, I guess you could say, the most common formulas. There's the Dubois formula, the Akers-White, which I will talk about later. Engel and Hansen, I'll talk about that too. Yang was also a good formula. Einstein is in there. Shockley's was a very granddaddy formula, maybe around the time of Dubois formula. Bagnold, Einstein Brown, Larson, Meyer-Peden, also Rands in here, Shields, and so forth. As you can see, there's variability. There's at least 1 order of magnitude variability. Let's not say at least, let's an average 1 order of magnitude variability. So if one of you gets an answer of 10 and another one's an answer of 100, that's not uncommon because that's still within 1 order of magnitude. That is the, how can I say, the nature of the beast in transport calculations, sediment transport calculations. There is a lot of variability.